Q is the total amount of energy, whereas H is the enthalpy or the heat. Remember that these are different from our first week on this unit. And so then finally we have our delta H, which is going to be our change in heat, and that's going to be per mole. So our total energy is going to be in kilojoules. Our enthalpy or our heat is going to be in kilojoules, and our change is per mole. So we're going to have a new unit here. Our unit is going to be kilojoules per mole, which we saw when we were writing the reactions on the previous paper. So in order to calculate delta H of a chemical reaction, we're going to take our Q, which is our total energy, and we're going to divide it by the moles that we have. And so Q is going to have to be in kilojoules so that delta H is kilojoules per mole. So let's look at the first problem. The dissolution of 5 moles of KCN. Dissolution just means the breaking apart. This is a decomposition reaction. It tells us how many moles of KCN, and it tells us how much energy this is going to require. So that's going to be our Q here. Since it's requiring energy to go in, notice that Q is a positive number. So we want to find out what the delta H for this reaction is. And so what we're going to do is we're going to basically, to find our delta H, we're going to plug this information into this overall equation that Q, which is our energy of our reaction, this is requiring 413.5 kilojoules of energy. Remember, Q must be in kilojoules, so we're good there. And then we're going to divide it by the number of moles that are reacting. So if we take 413.5 and divide it by 5 moles, that means that our delta H, or our change in our heat energy, is 82.7 kilojoules per mole. It is a positive kilojoules per mole because this is energy that is going into the chemical reaction. So take a minute and pause it. Remember, our delta H is going to be equal to our energy divided by our moles that are reacting. I'd like you to go ahead and pause it and try number 2, 3, and 4 on your own. Remember that Q must be in kilojoules, so make sure that you're always in kilojoules, and then you can calculate your delta H. So pause it now and try some on your own. So here's your setup for the first one. We are producing 1340 kilojoules of heat, so there's our Q, and there are 0.677 moles of methane that are being reacted, and so our delta H is going to be 1,980 kilojoules per mole. This is energy being produced, so we are going to have a negative sign in front of that delta H. Now, the next ones are a little bit more complicated because we are not given moles. So the first thing that we have to do is we have to take the 23.2 grams of sodium iodide and we have to convert that into moles. So remember from our stoichiometry unit that 1 mole of a material is equal to its molar mass that we look up at on the periodic table. So the molar mass of sodium iodide is 149.88 grams. So that means that we have 0.155 moles of sodium iodide. So now we're ready to calculate our delta H. Delta H is going to be equal to our kilojoules of energy, which this is 120 kilojoules of energy being released, divided by our moles, which is 0.155 moles that we calculated. So our delta H, our change in our heat of a reaction, is going to be negative 770 kilojoules per mole. So there's our answer for that one. Now number 4 is a little bit more complicated as well. Again, we have to take that 14.99 grams of sodium hydroxide and we're going to need to convert that to moles. And again, we know that 1 mole is equal to the molar mass, which we can figure out by looking on the periodic table. So the molar mass is going to be 0.375. I'm sorry, our molar mass is 40, which gives us 0.375 moles. So now we can calculate our delta H. Now we do need to convert joules into kilojoules. Remember that there is 1,000 joules in every 1 kilojoule. So if I take that 18,300 and divide it by 1,000, that means I have 18.3 kilojoules, and I'm going to divide by my moles that I calculated. And so that's going to give me a delta H, and this is energy being produced. So I do need a negative sign because energy is coming out. So negative 48.8 kilojoules per mole is what is the heat of the reaction for this one.